Hello everyone, I'm Jim G from Electrical Computer Engineering at Texas A&M at Qatar. I'd like to thank Professor Ali for inviting me to your math class. Today, I'd like to talk about X-ray computer tomography, or CT. You probably heard about CT, but what CT is based on is typically X-ray. Now, X-ray is very interesting because it can see through the human tissues just like the light, the visible light, can penetrate a jellyfish. So I'll start with some basic introductions of X-ray imaging systems and CT. We'll talk about the physics behind it, and then we're going to focus on the mathematical models of the CT imaging and how do we use that model to reconstruct the images that you see in the radiology or in the hospital. And then I'll end this with some interesting facts. Okay, so you probably have done a chest X-ray or a dental X-ray. These are called the X-ray radiography. So in this kind of system, basically you have X-ray source which shine X-ray beam and which goes through an object like a teeth or your lung, or in some case like in sport medicine, often it's a part of your body. And on the other side, there's X-ray detector. X-ray detector acts like a camera because it sees the X-ray, and then it will show the X-ray on the camera, and basically you have a 2D images of a 3D object. In this case, is arm. Okay, and you can see a fracture on this arm on the bone. But what is the CT? CT stands for computer tomography. Tomography has two parts. Tomo is a Greek word which means slice or section of something. Okay, you cut a bread, that is a slicing. Okay, and a graphin means write or record. So photograph, photography means the art to record a photo. Okay, so tomography is a term that we use often in medical imaging or radiology that generally refers to any of the imaging method that makes 3D images of internal organ from a large number of 2D X-ray views taken at different angles. What you see there is a CT machine. As you see, there's a big cylinder which is for patient to go in, and there's a platform for you to lie down. And inside this big cylinder is all the parts of it. Okay, so when you see a CT image, you wonder like all this bright and darkness, what this actually means. Let me start by telling you these are actually a map of X-ray attenuation of the organs. So the images we see it consists of many little dots. Okay, each dot is called it's a picture element or pixel. So the bright dots, like the bones, means they have a high X-ray attenuation, and then the dark part, like the air or is a gray part of muscle, they have a less X-ray attenuation. For us to understand that better, let's think about sample model. Let's say you have a X-ray beam shining from one side, and then you have a tissue, a sample here, maybe representing an arm or something, a sample here. So sorry. And then on the other side, you receive that, okay? And then we can receive the data in different ways. But today we'll talk about the very simple method, the most straightforward way of acquiring these images, which is called a parallel beam CT. The way the parallel beam means is you're going to shine the X-ray just like this. You in parallel. You go through the object, and the other side you take a view. Okay, you receive the X-ray on that side. It's called different views. And then once you take a view, you typically rotate the X-ray source and camera. You take another view. You take another view. If anybody have ever done an X-ray CT scan, you probably heard some like a noise, like a rotating noise, a gantry inside the big cylinder. You see, shoo, 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 shoo. This is a rotation of the X-ray source and the camera. Okay, and so to model this process, let's think about a very simple tissue model. Let's say here you have this shaded slab here. Let me try to make a mark on this. This slab here in the middle here, these are a model for like a piece of a muscle, and you have an X-ray coming from the left side. Okay, let's say G represents the number of X-ray photons, and while the X-ray goes through the slab, some of them will be absorbed, so they'll disappear. The others will actually be scattered. It's going to a different direction. So on the other side of the slab, the detector, X-ray detector, will detect number of photons. Okay, and those number will be reduced because the reason I just described. So the number of lost photons, we can see delta G. Okay, the reduced number photons. Can be modeled as a product of mu, G, and delta X. Okay, with the mu here, the first term here, this is a constant that we call linear attenuation coefficient. This is a tissue property. So a bone typically has a large attenuation, and tissue has a smaller, muscle has a smaller attenuation, and then air has a very minimum attenuation. And then G is the number of photons, and then delta X is the thickness of this slab. Okay, very intuitive. So if you have a large number of photons to begin with, then you lost more. If your slab is thicker, then you lost more. If you have a higher attenuation coefficient, then you lost more. Okay, so now coming to something related to the calculus, is we're gonna make that thickness infinitely small. So we make that going to dx. Okay, and so if you have a large piece of muscle, then that G will be depends on the location. Okay, the depth of the muscle where you're looking at it. So it become a function of the depth. So G of X. Okay, and so this model here we have on top now become this equation. So delta G become a dg. And the mu also of tissue property that is depends on the location, so the function for x, which is the depth, and then gx and dx. Okay, that just turn that discrete model into a calculus model, basically differential equation. Now, so with this, we can start to build something even more interesting. Let's say you have this is a piece of organ, and we're gonna let the X-ray going from here to start with, This is the x, so represents the depth. So at any location here, you have the number of actually photons still existing and going forward. And so the thickness of every location, of course, we're going to call it dx, infinite small x. Okay, and we're going to make a simplification and say at any x, the tissue all has attenuation property for mu of x. And we're going to say in the beginning, we have total number of photons at G naught. Okay, and then with the previous equation now become, so dgx equals to minus mu x gx dx. Okay, and so you can change this to dgx over gx equals to minus mu x and dx. I hope you probably already learned this. Now the solution to this differential equation actually will take this form. Okay, it will look like gx equals to g naught, which is the initial number of photons, and then e to the minus, then you integrate the attenuation coefficient along the path dx. Okay, so over this whole organ, and that gives you the number of X-ray photons at any particular location x. So in the physics, X-ray physics or radiology terminology, we actually use we don't use the G, we actually use X-ray intensity, which we usually call I of X. So this is X-ray intensity, but just for you, just think this as if number of photons. Okay, so we have to get a little bit geometry. I know this is a calculus class, but you do need geometry to solve some real world problem. In this case, so let's say you have a brain slice, you're looking at it, and you shine a parallel beam in this angle theta, and each of the ray here can be specified by the distance to the origin, right? So let's say if you look at this this ray at this location here, then there's a distance from the center, which we call a rho, and then the rotation angle is the theta. So a pair of a rho and the theta specify a particular line. Okay, and as you can see very easily, this is actually a polar coordinate. Versus we have x, y, the Cartesian coordinate. There's a one-to-one correspondence between this. And then the total attenuation you accumulated along on the other side, you shine this ray, at any particular location. In the real application, of course, your detector has a finite element, so you only have discrete locations, and the angles, you also just take a finite number of angles, so there's a J and K, just indicate those detectors and angles. Okay, but at the moment you can think about this as a continuous value, so the detected signal here, okay, along that particular X-ray path is actually related to the ray sum of the attenuation coefficient along that red line. Okay, now what is a ray sum? Ray sum basically means you sum up every value along that line. Okay, so here's a practice for you to do maybe after class. Is if you have this like a line here specified by the distance to the origin by rho and angle with x-axis theta, how do you describe that straight line? Okay, and I don't have time on this, but if you work out the math, the equation describes that line, the dark line, or the ray path is x cosine theta plus y sine theta equal to rho. Okay, so you can use this, and together with the physics we just described, and you will know that, this detected signal, the GU theta k, actually will be the initial X-ray intensity, then e to the minus integration along that ray path of the mu xy integrated along that path. Okay, I can write this as an integration for delta function, but I think at this point I'll stop here. So as long as you have the intuitive understanding that the detected signal will be related to the ray path sum of the attenuation. All right, with that, then we come down to how do we use this model to reconstruct an image. If you have the views at different angle theta, you have this views at different distance to the origin. So there are, in principle, 3 ways you can solve that problem, which we call algebraic reconstruction, which I'm going to go through in a little bit detail. And then there's a direct Fourier reconstruction, which is related to the Fourier transform. So you will need to learn Fourier transform anyway in the future, but we don't have time to get into that today. But then finally, there's a third method, which is called a filtered back projection. It's actually quite easy to understand on the conceptual level. That is a method that actually being used mostly in the clinical scanner. So I'll just give a quick intro, and let's see, how do you do the algebraic reconstruction? Okay, to understand our ART, I'm going to use a simple physics model example here. Let's say you have a tissue in the like this block. Okay, so I'm gonna simplify this and divide it into 4 little cells, and I'm gonna say each cell has a homogeneous attenuation, which I say mu1, mu2, mu3, mu4. Okay, and then I'm gonna say that the size of this little cell is x squared, so it's x times x. Okay, so now let's look at the physics model that relate to the initial X-ray intensity I naught to the detected X-ray intensity on the other side I1. I'm going to look at this first ray path here. Okay, so I1 equals to I naught e to the minus integral of the attenuation along the path. Since in this case we have simplified the model, and that integration will just become a minus mu1 time x and mu2 time x. So I'm gonna just add these 2 together and say mu1 mu2 time x. Okay, and you can do another equation related to I naught with I2. And so on and so forth. Okay, in this case, I have 3 views, one from 0 degree, then another one from 90 degree, and then another one going through a 45 degree. And you can have this at least 7 equations. Now, in these 7 equations, you basically have 4 unknowns, and you can solve these equations. So you have enough information to solve them. And but to solve this first, we have to make some equations that we can deal with. So I'm gonna use this first equation as example here, there. So I1 equal to I naught, then e to the minus mu1 plus mu2. These are attenuations for the two cells, and x, which the width of the cells or size of the cells. Okay, so I can take this is a nonlinear equation. To solve it, I can take a log on both sides. Okay, and then this equation can be very easily simplified as a log I naught over I1 divided by x equals to mu1 plus mu2. Okay, so you do the same for the second equation. You're gonna have something relate to the I3 plus I4, and that's related to the I naught and I2. So so on and so forth. You do this for all the equations, and you're gonna come out to a set of linear equation or a linear system that relate the unknown, which is mu1, mu2, mu3, mu4, with the data that you acquired. So that first equation, remember, we have a log I naught over I1, and this is the equation for this is so 1, 1, 0, 0. So mu1 plus mu2 equals 1 over x log I naught over I1. So for the second equation, you get mu3 plus mu4 equals to the not over I2. So you can keep doing all the other equations, okay, as long as you have more than 4 equations and they're linearly independent, then you can solve these equations by doing a matrix inversion. Okay, so I'm gonna maybe so you can take a matrix inversion on here. So hopefully let me erase this so you can see a little bit more clear. Okay, what I mean here, so this is set x, these are unknowns, but these are really just the attenuation coefficient. Okay, so solving this set of linear equations, you can get a map of the attenuation, and then your image is reconstructed. Now this is very easy to do in this simple example. You only have 4 unknowns, but as you know, in a real X-ray image, you can easily have 10,000, even 100,000 pixels if you have a high resolution X-ray. So you basically have a 100,000 equations to solve, and take an inverse is difficult. Okay, fortunately there are numerical methods that allow you to solve these equations more efficiently. These are in a little bit advanced algebra courses, so I will not get into details, but I just want to tell you this is actually very common in medicine, medical imaging, in communication, in many other problems that you need to find a solution of a large linear system. Okay, so I'm gonna skip the Fourier reconstruction and jump into the last method, which we call filtered back projection. Now, what is a back projection? Okay, so when we take the views of this object at a different angle, this is actually called a projection. The shadow you see is a projection. Okay, it's a forward projection. Now, a very intuitive way of reconstruct the image perhaps is to do a back projection. Okay, so you see the shadow at a 0 angle, then I just back project at the shadow, so I get the strip here on horizontal. Then for the vertical, I'll take a projection, so I back project that shadow, and then I get this, vertical strip. And 45 degrees, the same thing. As you can imagine, if you have this from many, many different angles, you back project them together, hopefully you will get something similar to the object, right? You start with. Um, Now, unfortunately, this is very intuitive, but it's not mathematically correct. Again, I don't have time to prove this. If you're interested, you take a medical imaging course. I'll show you a full proof. And turn out the correct way to reconstruct this is you have to do first a filtering operation. Okay. Now this filter actually is a high pass filtering. Okay, if you don't know what high pass filtering means, take a digital signal processing. Basically you do a high pass filtering on the individual view or projection, and then you do a back projection, and now you will be able to, if you have enough projections at different angles, you will have a very quite faithful reconstruction of the object that you see here. Okay, and this is, as I said, is a workhorse. This is a workhorse algorithm in the clinical scanners. So CT is, I would say, this probably the second mostly used tomographic medical imaging method. The top one actually is ultrasound because it's very cheap and convenient, portable to do. But I would go second method probably is X-ray radiography and X-ray CT. It has many applications. I can't tell you all, but we use X-ray to do mammography. These are low energy X-rays to detect the calcified knots in the breast for early detection breast cancer. Anytime you have a bone problem or cartilage problem in your joint, you can take an X-ray. You can use X-ray to visualize the GI tract problem, some solid tumor, and the spine problem. We often use X-ray CT. Interestingly, we can do a dental X-ray, and you probably also know that when you go through X-ray airport security, sometime I don't think we do this in Qatar, but in the U.S. and China, sometimes they will pick you to let you do a X-ray scan, let you empty your pocket, raise your hand. There's a scanner. It goes through in front of your body. Okay, these are called a backscattered X-ray. It again use a low energy X-ray. It can see through the body surface. Okay, so if you're hiding something beneath your clothes, it will see. So you can request a different way to scan that, but it's very fast, it's convenient. Now, all these X-ray, now oftentimes people concerned about X-ray CT that will give you some radiation. Okay, I got a news here. This is 2013. There's a nuclear due to the tsunami in Japan. In Fukushima, there's nuclear fuel leaking, and it gives a lot of radiation. These are nuclear fission radiation, which emit gamma rays, okay, which has a much higher energy than X-ray. But nevertheless, X-ray still gets you some ionizing radiation. And in Qatar, just as in anywhere else, we see an increasing number use of CT in the medical practice. So this year I didn't travel much, but still, I had a X-ray on my shoulder injury. and I had a couple of them when I go through travel in early spring, and I'm gonna have another travel, in the winter break. So I get some X-ray exposure. Okay. So naturally, you may ask, oh, I also got X-ray when I went to see the dentist. So what would be the best shield against X-ray radiation? Thought about that question? Okay, give you some answers. It turns out that any of the heavy metal with a high atomic number, they typically have high X-ray attenuation, means they can absorb the X-ray, so they will not get in your body. Lead is a perfect example. Gold is another example. Okay, so when you see the Star Wars movie and Darth Vader, wear um, these armors and has some scientific meaning. Okay, because these guys do a lot of stuff in the interspace travel. There are a lot of radiations, gamma ray radiations out there, so it may shield some X-ray, some of the gamma ray radiation. Another interesting thing that has a very, very good X-ray shielding property is actually the diamond. So next time your girlfriend or wife asks you to buy some jewelry, yes, this can be beneficial, okay, in addition to the beauty. Okay, I guess I have to conclude. So we talk about X-ray CT and the mathematics and physics behind it. You already see that we basically do reconstruction by either solving equations or using some other mathematical operations of filtered back projection. And I can't emphasize more that mathematics is so important for engineering, particularly in electrical engineering and computer engineering, because every disciplines, like the area I work on, medical imaging, but also telecommunication, cybersecurity, machine learning, artificial intelligence, it all involved heavily mathematics. So I hope you enjoy learning math, and I hope to see you, some of you at least, in the future, and to learn how to apply the math you learn in this class to solve engineering problem. And good luck with your math, and I'll see you around in campus sometime in the future, hopefully. Best luck for your study.